As you see on the presentation slide, the title is Distributed Caching Patterns in Kubernetes. So I'm going to talk about all the buzzwords that you can find on the internet, where you can put into your CV just to increase your salary, etc. So those are trendy stuff. Okay. That's about a bit about me. So I'm lead engineer at Hazelcast. As a Java developer, lived in several countries, and this is my Twitter handle, which you can follow. So the agenda for today is I'm going to give a brief introduction to Hazelcast, and I'll go through some caching patterns, and then once you implement those caching patterns in both Monolith and Kubernetes environment, I'll just explain how you can deploy those into Kubernetes, and then after the deployment, how you can manage it as a day 2 operations. So a bit about Hazelcast. Hazelcast is an open source company. The products that we have is Hazelcast IMDG, is in-memory data grid, which I'm going to talk about today mostly. And Hazelcast Jet is stream processing engine. Hazelcast Cloud is hosted managed service of Hazelcast. And the management center is monitoring and management tool for Hazelcast IMDG. And it's closed source, but it's free up to 3 Hazelcast member cluster. So those are all, not all. Hazelcast IMDG and Hazelcast Jet is open source products, Apache 2 license. They are fully hosted on GitHub, so you can go for contribute. So pretty much you can do whatever you want. Hazelcast raised some money recently. You can check career website. If you see any suitable position for you, then you can apply. It's a remote company, so you can work remotely. Why distributed cache? So there are 2 keywords here. One is cache and the other one is distributed. People are most talking about data-intensive applications nowadays. And in data-intensive applications, you have data where you store in some backing store, data store. You do use some query language just to make some query on top of the data. You do batch processing, stream processing. But you also need to do caching if you need high performant microservices or application, because caching is using memory, and memory is faster than reading from storage. So that's the main reason. And the distributed part, the second keyword that I use here is that in cloud native applications. So if you move from Monolith to microservice, then you will just end up having a distributed environment. And your solution, your caching solution must be distributed. And Hazelcast is a very natural fit for cloud native deployments. So those are the reasons why you need to have distributed cache. So this is basically a simple diagram which tells that random access memory is faster than storage if you just check in detail. So caching patterns. So what kind of caching patterns you can use in applications? So basically there are 2 categories that you can see. One is cache as a site, where you are basically using a cache and dealing with the cache yourself, and you directly interact with your database. This is cache aside. So if you go and check your cache, if it is cache miss, then you go to database, put the data into cache, and next time when you check the data, it's gonna come from cache. The second category is cache as a SOR, system of record. Actually, in this use case, in this pattern, you directly deal with the cache, your caching solution, and the synchronization between your cache and data store is done behind the scene. So you don't have any direct access to database. You directly use your caching solution, and then your caching solution is doing all synchronization with data store. There are some different patterns in the cache as a system of record: read through, write through, and write behind. So if we go and check the read through cache, for instance, in this picture, as you see, on the left side, you have this application. It's actually a microservice, we can call it. It does a map.get, it's just a lookup. It asks Hazelcast cluster if that data is available. And Hazelcast, if it's not available in Hazelcast, it just goes to backing store, data store, fetch the data, put into cluster, cache cluster, and then return the data back to the application. In the subsequent calls, your data will come directly from cache, which is much faster. So this is a basic read-through cache. For write-through cache and write-behind cache, this is for writing to your data store. It can be sync or async, but it's again behind the scenes done by Hazelcast. So how is data partitioned in Hazelcast? As you see, there are 3 members here in the cluster, and on the right side, you see that this key value 1 and Minsk key value pair is in this member, and there is another member keeping the same data as a backup. So Hazelcast by default keeps 1 backup in the cluster. You can increase that value up to 6, or you can even make it 0, but it is by default 1 backup. So what does it do? So in 1 backup, let's say that the member which is holding the backup data, if it crashes, then this primary data will be creating a backup and sending to another member. So and if the primary data is crashing, or this member just you kill it via it can be a failover use case, or you can just shrink your cluster, then this backup will be promoted as a primary, and it will send the backup to another member. So this is basically how partitioning is done. So you are free to kill in 1 backup count. You are free to kill. You are free to kill any member you want, and then you will not lose any cache. Okay, so how can you use those stuff in Kubernetes environment? So I listed 4 use cases for patterns that you can use in Kubernetes environment. One is embedded. The other one is this very famous Kubernetes sidecar pattern. The other one is proxy cache, and the last one is client server. Okay, so for the embedded, that's the simplest one, and the first one I'll leave you a bit second just to see the diagram, because all the other diagrams are similar to that. So this is pretty basic Kubernetes environment. So you just get the HTTP request, and is terminated by Kubernetes service, which is a load balancer, and then this one is sending the request directly to your microservice. So when you receive the HTTP request in your microservice, in this pattern, each microservice is starting Hazelcast member inside the Java virtual machine. So in that sense, it is an embedded. So the beauty of this one is that you don't need to depend on any external cache server, cache cluster. That is good, but it can be bad at the same time, because you might not want to keep your cache data inside your microservices JVM. So that's one disadvantage you might not want to use. And the other one is that if you scale in Kubernetes environment your replicas, so those microservices are stateless. If you scale, let's say that up to 100, you will end up having 100 member cluster in Hazelcast, which normally is not needed. But if you know what you are doing, actually, then that's the simplest one. You can start with that, and then you can switch the other caching patterns too. Okay, so embedded is simple, and it's Java only, and data collocated with microservices JVM. So the other caching pattern that we see, and Kubernetes sidecar pattern is, as I said, very trendy nowadays. Is sidecar pattern is very similar to embedded, but you can use multiple programming languages here. That's one advantage. And the other advantage is actually you can specify CPU and memory limits based on your requirements on different containers. That's something you can't do in embedded mode, but in sidecar mode, let's say that you can give 4 GB memory to Hazelcast member, but less to microservices. Or you can define your CPU requirements also in the same way. So those are the advantages, and the other advantage is that it doesn't depend on any external service again. Okay, so those are the benefits of the sidecar, and multiple programming languages and data collocated within the microservices pod, not the Java virtual machine. Okay, so next one is HTTP reverse proxy caching. This is something we don't have, but you can implement internally inside your company also. So in this case, your microservice does not have to know anything about caching, does not have to have any caching API inside. You basically inject your caching into the microservice, and you can enable and disable. It's like an aspect-oriented programming, cross-cutting concern. So that's basically what service meshes are doing right away with Envoy, for instance. But Envoy doesn't have a caching abstraction yet. There's a pull request waiting to be merged. When it's merged, probably, yeah, you will use Envoy. If you are using any service mesh or service proxy, then you can plug, when we implement the integration, you can plug Hazelcast into that. But the advantage of reverse proxy caching is, as I said, you don't have to implement anything inside your microservice, any caching API, and basically you are injecting that feature into your microservice. So the other one is client server. This is the mostly we see in open source community and users that deploy into production. The main advantage of this one is that you basically separate the microservice layer from your cache cluster. So then they are independent from each other and they are independently maintained. It can be by different teams or I don't know. So this is the advantage, and you can also use this pattern as a cache as a service throughout your organization, which means that multiple microservices can just use as a caching solution in this case. It's not as simple as embedded, as I explained, because you have a separate cache cluster, but this can be used as a cache as a service product inside your company. And in client server, there's another solution is using Hazelcast Cloud. Hazelcast Cloud is managed service of Hazelcast, IMDG. If you don't want to maintain Hazelcast cluster by yourself, then that's something you can use. It's pay-as-you-go model, and it's completely maintained by Hazelcast as a company. So you just go and start your cluster, and your microservices can depend on that one. So it's basically similar stuff that you see in multiple cloud providers that as a managed service. So similar stuff. So in client server, yeah, I think I've just gone through all of this stuff, but the main point is that you separate your microservices layer from caching layer. Okay, so I just put some code before the slides. So don't do it all the time because it can go wrong. So this is how you can use Hazelcast embedded mode in Spring Boot application. You basically, Spring Boot has very native integration with Hazelcast. So if you define such a bin, then your Hazelcast instance will be initialized by default. So this is embedded version in Kubernetes environment. You can do similar stuff for if you are using Hazelcast client. This is another configuration for Hazelcast client. If you have this config and your class path contains Hazelcast jar, then your Hazelcast instance will be there. And you can simply auto-wire it and yeah, start using a distributed cache with some basic stuff. So best T in the world is it's gonna print something. Yeah, I guess Minsk. So that's it. So up to now, it was mostly like how you can use as a developer Hazelcast as a caching solution, or maybe senior guy, some architect, etc. And once you decide to do it, then you have to deploy Hazelcast into Kubernetes environment. Then you need to have some kind of toolings and options to do that. So one option is Hazelcast Helm chart. If you use Helm install stable Hazelcast, it will by default deploy 3-member cluster plus management center. So you will just get a complete platform when you do just execute this command. And let's say that if you need to have some metrics, etc., if you say metrics enabled true, then each Hazelcast member will expose metrics in Prometheus format. And if you install Prometheus as well into Kubernetes environment, it will start directly scraping your metrics, which means that you can use some Grafana dashboards or you can use some auto-scaling features based on those metrics. So this is the simplest way to install Hazelcast into Kubernetes cluster. And open source community is contributing a lot here, so we are improving the intelligent defaults over there to make it easy for everyone. But whatever you configure in Hazelcast, you can configure in Helm chart too. You just need to change the values YAML in the Helm chart, and then you are pretty much you can pretty much do whatever you want. So this is one option. The other option is Kubernetes operator. Hazelcast Kubernetes operator is hosted on operatorhub.io. If you are into Kubernetes operators, then this operatorhub.io is created list of available existing operators in the market. So you can use operatorhub.io. But you can also use, if you are using some commercial Kubernetes distributions like OpenShift or IBM Cloud Private, then Hazelcast comes with directly catalog. So you can use Hazelcast from this catalog too. And the other option, deployment option, Hazelcast Cloud. So you can just go create an account and start using Hazelcast. Okay, so you have now the deployment options, and you decided to deploy Hazelcast. Some of the best practices that I'm going to throw now. And those are mostly specific to Kubernetes. If you don't know Kubernetes, you will at least get some idea what it is, then you can check after the session. Predictable resource allocation is is important. Actually, this kind of stuff is important in all of the all of the resource allocation stuff. So you need to calculate your requirements before the deployments. And this is even important in Kubernetes environment, because if you don't specify your resource requests and limits for CPU and memory, you are the first target by the Kubernetes to be killed in case you have resource issues in your Kubernetes cluster. So if you don't define this, then I mean you are very well eligible to be killed. The other option is to give, let's say, I want to have as a resource, I want to have 1 gigabyte memory, but I can go as a limit up to 4 gigabyte. Then you are the next target, because you are trying to be intelligent. You just request 1 gigabyte, but you say that for up to 4 gigabyte. So you are the next target to be killed after the first one. It's called yeah, I don't remember the naming, but you are the next one. The thing that we are offering here is that to set those values the same, then you are guaranteed by the scheduler not to be killed. So you are going to be the last one. So that's one thing. The other thing is pod anti-affinity. That's interesting one. So normally in pod placement in Kubernetes environment, Kubernetes scheduler can easily place two of your pods in the same Kubernetes node, in the same Kubernetes infrastructure, VM or bare metal. Which means that if you kill 2 members at the same time, or this node crashes, then you will lose your cache, some of your cache, and that might be costly based on your architecture, because you need to reload it from your system of record, database, etc. Instead of having such an issue, you can explicitly say to Kubernetes, don't place 2 Hazelcast member pods in the same Kubernetes node. And then Kubernetes will decide, will obey that rule, and then will do what you are saying. So this is pod anti-affinity, and it is important to use it. Okay, so let's go to the next one. So the next one is multi-zone deployment. So Hazelcast is very network latency intensive product. So network latency is important in that case. So you might not want to deploy Hazelcast cluster into multiple availability zones. But in case you decide to deploy it, which is very, very usual case in Kubernetes cluster deployments, some of the nodes are in one availability zone and some of them is in another availability zone, then you need to switch on zone aware. So if you do this, then normally on the right side, you have 3 members, and if availability zone goes away, as we said, there's a backup count 1 is by default. And if all 3 members just go away, you lose some cache. So instead of having that issue, if you switch on zone aware feature, all backups of the primary data located here, all backups will be listed here, and all the backups of those primary data will be listed here. So in case one of the availability zone goes away, you will not lose any cache. Your cache data will be promoted from backups on the existing availability zone. So this is another best practice that you can apply. So you just follow those best practices. There are some other things that you can follow too, and you decided how many members you're gonna install. You decided the resource allocation, CPU, memory, etc. But even if you decided everything perfectly, you will have day 2 operations, because not everything is gonna work the same way that is deployed. in the first place. So in the day two operations, is one of them is scaling Hazelcast cluster. So you start, let's say that with the Hazelcast Helm chart, you start a 3-member cluster with management center, but then your data size are increasing, and then you want to scale out. So those are the commands you need to use: kubectl scale or Helm upgrade, just to scale out your cluster. But you can scale in also with the same commands too. So you can go from 3 members to 10 members, and then you can come back to 3 members again using those commands. The other solution is horizontal pod autoscaler. So this is not a manual, but some kind of intelligent autoscaling based on your metrics. So there are 2 metrics types here. One is resource metrics, which is basically CPU and memory usage of your pods or Kubernetes nodes, and has nothing specific to your application. So if you are just good at with those metrics, then you can just configure horizontal pod autoscaler. You can say that if the CPU usage increases more than 80%, then just scale up to 10 members. So this is one thing. The other thing is custom metrics. Custom metrics with horizontal pod autoscaler. You can create your autoscaler based on application-specific metrics. Let's say JVM heap size, for instance. So that's something you can use with the horizontal pod autoscaler. But horizontal pod autoscaler will basically add or remove some pods. That's the thing. The other scaling option that you can use is vertical pod autoscaler. This is basically this old-fashioned scale up, scale down stuff. So it's basically restarting your Hazelcast member with more or less CPU or memory requirements. So vertical pod autoscaler is used in that way. So your pods will not increase, but each pod is going to have more or less resources. And cloud autoscaler is another one. So you basically autoscaled your pods, Hazelcast members, but then you end up having some VM issues or underlying infrastructure issues. So you can combine the pod autoscalers with the cluster autoscaler, which will initialize some new VMs based on, again, some metrics. So if you need to launch big cluster, then you can enable cluster autoscaler to just create some new underlying infrastructure. So those are the scaling options that you can use. And the other one is rolling upgrade. In rolling upgrade, you have in Kubernetes environment, you have options to do some zero downtime rolling upgrades. But why would you do rolling upgrade? So one option is one reason to do that is version upgrade. So Hazelcast version upgrade, you might need to execute in your environment. You might have to change some config parameters inside your Hazelcast cluster, and you might need to extend your Hazelcast cluster with some business logic. It can be some App Store implementations or entry processor. So those are requiring some restart. And how would you do the restart is, so Helm upgrade and kubectl set image, those are some options. Hazelcast Helm chart is using stateful set. If you know what's the difference between stateful set in deployment. It's basically stateful set is mostly used by data stores, which keeps some state out of pod restarts. Compared to deployments, because deployments are mostly for stateless logic. So we use this stateful set in Helm chart, but you can also use deployment if you know what you are doing. And in case of deployment usage, you need to set rolling update strategy. The reason we do this is because in Hazelcast, if you do rolling upgrade, you need to do it one by one. And each upgrade needs to wait a graceful shutdown of the previous one, and then it will start a new member. So this thing is because you don't want to lose cache data. And there's one interesting stuff other than this optimized grace period in Kubernetes. So Kubernetes basically, this grace period is 30 seconds. And even if you set graceful shutdown, if it takes more than 30 seconds, then Kubernetes will send a kill signal to the pod and it will directly kill the process. So you can be in a situation where you couldn't gracefully shut down. So you can optimize the grace period based on your architecture again. So we have something like 10 minutes in Helm chart, but you can do based on your architecture. Okay. So the last one is monitoring. You can use Hazelcast Management Center as a monitoring and management dashboard. And you can also, as I said in previous slides, you can use Prometheus in Kubernetes environment, and combining with Prometheus with Grafana dashboards, you can also monitor your metrics inside the cluster. And also metrics are used by horizontal pod autoscaler, as I mentioned before. And the last one is alerting. So instead of just monitoring stuff all the time, you need to define your alerting stuff just to be alerted on some urgent stuff, etc. So monitoring is important. Okay, I'm done with the slides. So thank you for listening. I think I can get questions.